Great to see everybody out there. Alistair, Brandon, thanks for joining. John, got Mike Hirschberg on the line. The whole the gang's all here. Hey, Mike, good to see you.
Likewise.
It's good to have 10 minutes between events to put your feet up on the desk, but you never look that relaxed. You're always getting ready for the next one. So I always like to, at the front of the meeting, give anybody the opportunity that hasn't been here before or in a while to introduce themselves, if anyone's interested in that. My name's Andy Mearns. I'm a business development consultant, and I used to sell corporate jets and helicopters. And now I help startups that are working on their go-to-market plans. Any other intros out there or projects that are
Dan
ongoing?
Newman. I'm back to designing aircraft. I worked for a little while at Honeywell as the CTO of the AAM group. Worked VFS years ago with Mike Hirschberg and on and off again. So nice to meet you. Look forward to promoting the community.
Outstanding. Thanks for being here, Dan.
I just wanted to mention, so Mike Hirschberg, I'm the Director of Strategy for the Vertical Flight Society, but I just want to mention we had a very, very successful symposium last week on hydrogen. So that was really good. And one of the sessions, which had the big announcements from United Therapeutics on their hydrogen-powered helicopter, and also the CEO of Zero Avia, that we've posted those videos available to the public. The other ones are just for people who attended the event. But I'll post the link to the page. And like I said, there's I think it's 2 hours or hour and a half of the executive keynote introductory remarks, which are very exciting.
Excellent. I look forward to checking that out, Mike. Thank you. Anyone want to, Stacy, how are you?
I thought I was so hard. We should come to meetings. I'm on the East Coast this week. For those who don't know, I'm with Corey, of course, Big Composites, great supplier. So just wanted to say hi real quick for this. Look forward to the talk.
Let you know your garbled. Your messages were a little garbage from the microphone.
Thanks for being here, Stacy. Yeah, Dan was just saying it was the microphone might not be the greatest. It's a little garbled.
All right, can you hear me better now?
Much better.
All right, it got my Bluetooth got twisted around. But anyway, Stacy Bill with Toray. Glad to join you guys. I'm on the East Coast this week, and look forward to the discussion today.
Excellent. Thanks for being here.
No problem. Thank you.
I'm on the West Coast this week. I'm out in Santa Cruz.
Well, you're almost in my neck of the woods.
Okay. Well, I got a demo flight from Domjan Zabavnik. We went to see him, and he and at his company's called Ivy, and he did a demo flight for us, which was really cool.
Oh, wow.
Out at the Marina Airport. Yeah, that was fun.
I haven't heard of them, so I'll have to look them up. That sounds exciting.
Well, about 2 or 3 months ago in this group, he did a presentation. So if you look at the at our website, and I'll drop that into the notes, you can find his presentation, and it's pretty cool. He's working on a very unique design UAV that I think will potentially blossom into something more full size after he's got some more test flying and substantiation. But it's a really cool design.
That's good to know. Thanks.
Yeah. Anyone else news about their company R&D or themselves?
Andy, I'll jump in. Tom Perkowski,
hey, Tom.
From Apex View, work with companies, help them navigate the government innovation ecosystem. Was at the event last week, the H2 Aero Symposium. I'll second Mike. It was actually a really solid event. Great presentations. I learned a lot. So it was a smaller event, so it made networking easier with folks. So that was kind of a difference from some of the other VFS events. Just kind of a thought. I was at Navy League last week. I apologize, my video is not working. I can't figure out why. So I've already restarted twice. But I was at the Navy League. Dan saw Andrel with all their amazing products displayed there, and hope to see them again at the AUVS Exponential in a few weeks, but generally a pretty solid show, on the Navy side of things. So it seemed like, there a lot of the brass were there and whatnot. The mid-level military wasn't there like they normally are in bulk, but so far so good in terms of positivity, at least on the Navy side of things. I'm hearing different things on the Air Force and others, but thought I'd just give you the guys that quick update, having just gotten back on Tuesday night from Sea Air Space.
That's great. Thanks for that, Tom.
Well,
On the topic of events, any H2 or others that anybody had comments about, past, present, or future?
Say we have our Forum 81 planned for Virginia Beach, May 20th, 22, and got all kinds of eVTOL and vertical flight sessions and discussions, and as well as almost 300 technical papers. So hope everyone can come.
That's your big one, right, Mike? How many people roughly do you pull in for that event?
Usually between 1,100 and 1,200, but we're not sure what the Army, Navy, and others are doing. But we're trying to get folks there.
It's big. That's as big as you get in the vertical space. And in terms of aircraft, will there be any aircraft of note that might be making an appearance?
Well, we're not a trade show, so Verticon is like, I don't know, 15,000
Yeah.
or some attendees, and they have 65 aircraft or whatever. So we're not a trade show, but yes, we gotten, I'll say, approval to get the V-22 to fly in. And then one of our companies, I think, is bringing a Robinson that you're using for avionics testing, an R66. So that'll be, Robinson helicopter, I should say.
Yeah.
So that'll be, those are the aircraft we're expecting to be there.
Yeah, perfect. That'll be a lot of fun. Awesome.
We had expected that the Army was going to bring their Rascal test bed, but they had to cancel that, unfortunately.
All right. Well, sure others will drop in. Any other events we should know about?
Just we have our electric aircraft symposium in July. That'll be the weekend before the big Oshkosh Air Venture. So I think that's July 19 and 20. So we're starting to plan for that, for all kinds of vertical, short, horizontal takeoff, hybrid, battery electric, and hydrogen electric review for this Saturday and Sunday.
That's a great one. I've been the past 3 years. I've enjoyed every one of them. Great networking for me, and I think for others as well. A lot of learning opportunities. And if you're thinking about going to Osh, you're already going to be going, but it opens up different, less crowded airfares and car rental opportunities because you'd be there a little bit earlier than everybody else. So it works out time-wise really well. So that's one I recommend as well. Mike, thanks for dropping the events notes in the meeting notes. Appreciate that. Well, we've got a great speaker today, and we're going to talk about batteries. And batteries is like, microchips in our business. It's changing, growing every day, and you gotta keep an eye on what's going on. And so we're going to be very lucky to have an update about batteries today. We're joined by Rodolphe Boulais, who is the technical lead at Saft for Emerging Aviation Products, for aerospace, defense, and performance in that division. Rodolphe, over the past 30 years, has held a lot of positions in the battery industry, working in quality, manufacturing, project, application engineering. He has contributed to several branches of the industry, including technology transfers, process improvements, to battery designs for electric vehicles, telecommunications, and aviation. He's a dual French and American citizen, and he holds a Bachelor of Science from the University of Montpellier in France and the Valdosta State University in the States. And he's also a proud active member of the Vertical Flight Society. So with that, Rodolphe, tell us what's going on in Saft and in the battery industry today.
Yes, thank you very much, Andy. We'll share my screen there to present and continue
And
this. Can you hear me?
yes, and I'll ask everybody. One thing I forgot is I always try to ask everybody to mute, just so we don't hear background conversations and so forth. We want to be able to focus on Rodolphe. So in a minute, I'll mute and I'll ask everybody else to do the same.
Okay, let me share my screen there. So the presentation there. Still wants to do it on 3. Thank you. Share. Clear. Can you see it?
Yeah, it looks perfect. We're seeing presentation mode. That's excellent.
All right. Thank you, guys. All right. So thanks, Sandy, for the intro. Definitely thank you very much, Mike and VFS. Always outstanding events. And so we look forward to discuss and continue the discussion. This is always the beginning, and we'll try to present some insights of what the industry is currently working on. So we'll do a very brief presentation of Saft and Total Energy overall before we look at the application that really drives the requirements from energy storage design point of view, and we'll dive a little bit in the weed of lithium technologies and try to clarify a few things and hopefully continue the discussions. And before we on the 4th points there, we'll present some roadmap. So Saft, if you probably come across 90 years in aviation, 100 years, 107 years really since it was founded. It's a specialty, as you noted in my title there, for space, air, aviation at sea and on land. So we do all kind of battery systems from ESS, cylindrical pouch, multiple systems. So you can see some batteries here for the F-35, for example. We have, and the battery in the center is the A350, to be relevant to aviation. So over 90 years serving, Total Energy is also serving very well for over 100 years in specialty fluids and petroleum, as you probably know, but producing sustainable aviation fuel, specialty fluids for cooling systems, battery charger for electric aircraft. There's several units in France right now, and Hutchinson, part of also Total Energy, is a big contributor to the industry with a whole lot of components for ceilings and different cabin materials and so on. To be noticed is the transitions of Total Energy from strictly petroleum company to a multi-energy provider. 2023, 20 terawatt hours. 2030, aiming towards 100 terawatt hours with a distribution 2050 that is over 50% electricity and natural gas and so on. So complete transition in support of the advanced air mobility and the electrification of aircraft. Saft presents
Uh-oh.
of battery systems and maintenance with part 145.
Hey, Rodolphe.
Yes,
we
sir.
locked up maybe a minute ago. Could you just repeat the last bit for the slide?
For this particular slide?
Yeah, your screen locked up for about 20, 30 seconds there.
No, I apologize for that. So yes, Saft international presence, from Europe, Asia to North America, is multiple sites and manufacturing locations for aviation batteries. Part 21G certified and part 145 for repair stations. combines, I think Saft has over 400 COTS for aviation, strictly on aviation product. Like for example, 3,000 systems for the F-35, 300,000 batteries sold for the past 90 years, in aviation. So a good long history of understanding aviation as overall. We understand the testing, we understand the requirements for EASA or the RTCA and NASA. We produce pretty much all the formats that from cylindrical, prismatic to pouch. And today we'll focus on pouch, as the aviation really always requires specific energy and high power density. So, but let's open the discussion to the requirements, right? So I mean, out of over 20 plus requirements when you're designing an energy storage systems, let's sort out this little piano here of dialing, what an application requires. So for an energy storage systems, the energy density will fly you the distance. The power will represent your lifting capability. Of course, safety is always prime, a prime concern for aviations. It's always there, and especially Saft and Total Energy. Cycle life for the business case, as well as much as calendar life and cost is key for any kind of requirements. So now, when you look at a VTOL application, so this is very conceptual. Load profile, it's represented in C rate, which is basically the capacity of the battery. So if you imagine a battery that is 100 kilowatt hours, you would have to have 800 kilowatts of power on a VTOL at first. So that's your scale here of C rates over the different phase. So it's not timed. Again, it's just to represent and to give the magnitude of energy, total energy, the surface of your red area there that can be as to be provided by the battery systems. So that's your energy here. The power, the peak power that is listed here in your on your y-axis there, and your different phase of flight. So VTOL, very big peak on takeoff. Flying is when you're flying wings like these actors, Archer, Beta, or Joby rather, and so on. So your wing flights requires much less energy, 2 to 3 C rates, and when you land, you're required to fight gravity and provide a tremendous amount of power. So imagine that you're at the end of your flights and you have to provide an emergency response, so you will lose part of your battery. Therefore, the peak power on the ESS will be even greater. So again, conceptual, but this is to show you the complexity of a load and the value of and the impact on the ESS. Okay, so in terms of energy power, a VTOL is critical. Of course, cycle life, because you want to have business case to be able to go multiple cycles, 1,000, 2,000 cycles to support your business case. When you go to show you the drastic differences between VTOL and CTOL, so conventional takeoff, wing, you're rolling to a takeoff. A little bit more energy, energy requires to take off, but not nearly as much as a VTOL. As you can see here in the shadow, your wing borne, you have a requirements of power load that is not nearly as much. Also lesser. And of course, when you land, you pull back power. However, if you were to need an emergency, avoidance and so on, you will need power. So there is some power requirement, but not nearly as much as the VTOL shadow, as you can see. So on the energy storage systems, that means that you're going to focus your design and the need of design into energy, power, and calendar life more than cycle life. All right, so same concept here. We'll provide the slide, but you can see the drift of for an STOL, short takeoff landing. You are kind of in between with more drag, therefore more power and so on. So this is the application, right? And you summarize all these guys side by side, and you can see the stare and compare. So now, what does it mean when you have all these chemistries that are being presented to us, right? We have the LFP, the iron phosphates. We have solid lithium electrodes. We have LTOs, lithium titanium oxide. We have NMC, nickel manganese cobalt, or NCA. So you have all kind of chemistries, and you can see structures are crystalline structures here. This 3D structure. This is a solid metal. Here you have lamellar structure. So how does that? And carbon graphite here, LMNO, silicon-based carbon. So similar to this one here, or even more exotic LVPF, lithium, vanadium, phosphate fluor technology, and you have also the sulfur that we can hear about. So all these chemistries, we hear these names, these terms, and how does that comes together into a cell, right, in the energy storage system of a battery. So first of all, you have to sort out your cathode materials, your positive electrodes, as you're in your cell, and your negative electrodes, your anode. So here you have a typical cell where you have a substrate with your cathode materials. That can be any of these guys, or separated by a separator, something to prevent short circuits. And your anode structure, that it will be the recipient of the lithium. So the lithium technology is called the rocking chair technology. For that reason, is because the lithium shuttle between your cathode and your anode. So this is your discharge state. When you charge it, the lithium comes onto the anode side, and vice versa. When you discharge, the electrons come out. Lithium goes, and as an ion form again, and is going to your cathode. So each chemistry has a specific characteristic, okay, as just its composition, chemistry composition, and redox values. You see different voltage values, right? So those are the cathode values, and if you expose it to a different anode, then you have a resulting behavior at the cell level. So all this will impact your design and your capability to deliver energy, power, or cycling ability. So let's look more into the voltage side. So you have chemistries that we saw earlier. This is against lithium, okay? So it's against lithium metal, which is kind of a reference electrode in a way for this. So this is just the cathode side, okay? But you can see a huge variability of voltage behavior throughout the discharge, right? When you discharge your capacity of your battery. You see LMNO very, very high. So that kind of signal a very high energy capability, because, power is voltage times current. So if you have a very high voltage, naturally you have very high energy in your system. LVPF also, that is kind of sticks out and is very interesting. And you have the more traditional NMC or LFP that you can see evolve at very, very different voltage. So how does that impact, your production of energy and your storage of energy? This is what we're kind of like to present, like a heat map like this. So now you have the cathode materials that we presented with the anode materials, and together in a cell, how does that compare to a scale of VTOL energy power requirements? Okay, so this is really a VTOL, that's a VTOL graph. So you can imagine that you can do a heat map for CTOL and STOL. Again, that's a continued discussion. So you see a lot of really bright green and sulfur, but you also see a lot of red, and that's because the shuttle issue with sulfur has not been resolved yet. So cycling ability is not very good. The lithium metal on the anode side, same. The dendrite formations, very high power, technology readiness. All these criteria there are not resolved in a heat map. So what you're left with is chemistry, and this is why you're seeing those NMC and LMFP compounds being considered and being used right now for flight. Same for the anode side. You see a lot of graphite, you see a lot of silicon graphite technology. Okay, so you have a great candidate. The LTO would be great, but lower voltage, not good energy, very heavy technology, very expensive. So that's why you don't see too much of the LTO in those chemistries. Okay, so again, this is to continue discussions. When you present this into not just the cathode and the anode, but as a cell construction, you have these resulting criteria of energy, powers, safety, cycling ability, and you can see the impact and being able to compare these different chemistries and blends of chemistries. Never consider one chemistry being completely pure. Okay, you always have blends. So those are for their processability and to optimize criteria of safety. So I'll show you the results of these kind of blends and decision making. But to go back to our application and to aviation and VTOL specifically, you can see that the solid state is kind of out of the discussion, unfortunately, for reasons of power capability and maturity and cost. LMNO, same, great voltage as we saw earlier, but the complexity of electrolyte stability for these chemistry at very high voltage hasn't been resolved for the past 30 years. So that makes it difficult. So this is why if you compare these chemistries here, I've removed these guys as primary candidates because again, maturity is not there, power is not there, so or energy capability for LTO is just not there. Notice also that there are certain formats that are not really proper for certain chemistry, not proper for certain format, like solid states, very rigid system, not very good for cylindrical cells. LTO can generate some gas, so having a solid construction on the cell design, pouch or cylindrical or prismatic like this, like the PHEV2, typically is favored. So go back, now what are we using today is those NMC, NCA with graphite anodes. We also use a silicone anode base, which improve the energy and power. However, it degrades the cycling ability and with more reactivity, its safety it also gets challenging. But beyond a certain point, the UCAR, the evaluation of safety is just abysmal. Maturity level also is is a little bit of a challenge with silicone-based technologies. They're newer than the pure NMC graphite. So right now, a lot of candidates are using this technology. Past few years, over the past 15 years, Saft has developed a lot of lithium manganese iron phosphate blends. So it's a chemistry that is blended with NMC. So you put NMC and LMFP on the cathode side and graphite anode, and you obtain a little bit more balance. I mean, a lot more balance. In terms of safety and radar overall radar chart there that you can see. If you bring in silicone into your anode, so you improve your energy power. However, you start degrading your cycling ability and safety quite a bit. So those are the challenge. That's the optimize and compromise well-known statements in battery aviation. So you have to constantly look at your application, your requirements, and what is the need and what chemistry can satisfy that need. The future, very, very interesting with some chemistries like we saw with the voltage curve of the LVPF that's being super high and good cycling and good safety behavior as a very good candidate. However, this guy that chemistry, the lithium vanadium phosphate fluor, is not very the supply chain is not completely developed, and so the maturity of this technology is still a little bit away. So talking about supply chain, just few bullet points here. The sourcing origins are, with the geopolitical issues that we're experiencing right now, reinforce this message. To secure supply chain is very difficult. Qualifying a given chemistry, those extremely complex blends, on the cathode materials or on the electrolytes. All this has to be qualified. Take tremendous amount of time and effort to do these qualifications. So having the right suppliers and qualifying alternate if they, if one fail on you, because that will stop this. It's a very very important fact. The maturity. I mean, there's all kind of very novel concept and possibility, but how mature it is in terms of processability or scalability of your chemistry, and that will condition the RAMs of aviation: reliability, availability, maintainability, and safety. Those are key points, and the supply chain definitely is a key points on that. Just to summarize, really, and what Saft has sorted out for the advanced air mobility, and based on these requirements, is so LMFP blend graphites was really good energy density, specific power capability, and cycling ability is really good for this kind of application. We're talking here 100% depth of discharge in terms of cycles here at 1C, 1D, one rate of discharge, one rate of discharge. But again, to refine, so in applications and a true AEM cycles, we need to have the application to understand that. The UCAR level, the safety level, reactivity is outstanding. The cathode being so stable thanks to the phosphate that stabilizes this 3D structure is almost out of the equation here. This is kind of the pie chart of energy release of a cell, cathode, anode, and electrolytes. So even though you're not releasing, you're not removing the risk on your anode and electrolytes, by not having the cathode collapsing on you, you're stabilizing your chemistry. So again, and those are very mature technologies. Those are manufactured. I mean, we're providing samples as we speak on these, for the past few years on this chemistry made on production line. So now, if you place silicon in the anode, you obtain a gain of energy. Power is also gained. However, you have degraded the cycling ability as we discussed. So, and you regain a little bit more reactivity on your anode, even though you stabilize your cathode. Therefore, your safety criteria are and your reactivity has increased, has been degraded. A little bit less mature technology, but nevertheless, this is under very high scrutiny and evaluation and production. The last one is this guy here, which is, if you compare pure NMC on the cathode material, so now you release all your energy, and then stability of the NMC. You've placed high silicon content on the anode, so very reactive cells, just as pure NMC. There's no magic here. Your cathode is, as a 2D structure, not 3D, so destabilization there. High capability to host the silicon on the anode, and you obtain outstanding technology, a specific energy density of 300 plus watt-hours per kilo, 2000 watt combined, and 2000 watt per kilo, and achieve the 1000 cycles minimum. But it's a drastic change with the UCAR 6. It's drastic change from the LMFP blend, which offered 2500 cycles, and UCAR 3 and 4. So the proverbial battery, you know, selections and optimize and compromise is just there. So that if you summarize this, and this is the roadmap that we present to our customers and to the industry, with samples of this chemistry available for you know, to be added. So I mean, this is hopefully opening a discussion to more. Clarified a few things that may have hopefully not complexified, but that those are the work that we need to do to, you know, to understand the energy storage systems in an aviation system. I provided a lot of links in this presentation. So when you receive it, you know, I strongly encourage you. Of course, VFS is there. The Volta Foundation does a great job to present. So hopefully this will help you with some more resources on you know, to continue your journey of selecting technologies and battery, and contact us if you have any questions.
Outstanding. Excellent update. Thank you, Rodolphe.
Thank you, Andy.
Should we open the floor up to questions? I see Brandon's got his hand up.
Thanks, Andy. Honestly, great presentation. I love it.
Thank you.
A couple of questions from a bit of a layperson, to be quite frank. My battery folks are pretty smart, but LVFP technology, so not mature yet. What are some of the leading companies, and talk to me a little bit about. I mean, the curves look pretty enticing there. So who's leading the way on this, and when do you anticipate these type of cells to become available? Followed by, if we had, say, like a, you know, high C rating requirement in the 8 to 10 C, you know, range, for example. We can talk about that all day long, because maybe you buy a 20 C battery for a 10 C real application in the real world. But what, if any, sort of limitations might there be on that technology?
So we are involved heavily in developing that technology. Lower TRL, I would say it's still, you know, 3-4 TRL for this technology, mainly because of the supply chain. Okay, so your limitation is there, the availability of actors. You know, we are one. You know, I'm not going to present other actors, but we're investigating and qualifying this. I mean, in terms of capabilities and modeling and so on, to understand that chemistry. The supply chain is the big issue. So the vanadium production is, you know, is kind of an artifact of other industries, but to you know, to produce that, so the need and the interest of the industry, and possibly its commitment to develop the supply chain, would create that technology availability, because it has power capability, it has good stability, and cycling ability is very decent, and as you saw, the voltage is very attractive, and you know, the very high voltage evolving almost flat like the LFP across this charge state is very attractive. So it's being evaluated for different technologies, for different markets and capability, and we can discuss more. Since it's being developed, we'll have to place more NDAs and, you know, one-on-one discussion, but we'll definitely a good chemistry for the future.
Yeah, I'd like to speak with you maybe offline. What sort of rough C ratings could you anticipate out of such technology? And I understand that I think Australia produces the majority of the vanadium, so that shouldn't be too crazy from a supply chain. So maybe offline we can talk about why that's a challenge.
Yeah.
Okay. What sort of C ratings are you anticipating?
We see it applicable for VTOL.
Okay, so in the 8 to 12 C range.
Yeah, 10 C. Yeah.
Okay. Great. Again,
But again, it's like you mentioned, the C rate is conditional to the cell size, right? So we need let's talk more about that's why I prefer to use specific energy, specific power capability. The 250 to 300 watt hours per kilo and the 2000 watt per kilo. I think is a more it's a better gauge than the C rate, because if you have a very, very small cell, versus a large cell, it makes a big difference.
Yep, I'm completely understood. Thank you.
Rodolphe, if you want to disconnect the screen sharing, we'll be able to see you a little bit better too as you speak.
Oh, sorry.
And no worries. Perfect.
Thank you.
And then what other questions are on people's minds? Rodolphe, are we looking at sort of in the order of 1,000 cycles before we start to diminish the battery's capacity?
Yeah, and back to the discussion, and I think the very relevant discussion with application. Okay, those are industry performed, industry standard comparing technology to technology. So we tend to do 100% depth of discharge with our charge mode, the rest period that is, that the scientists see as ideal, and the but it's 100% of the capacity discharge, 100% recharge, which impact a lot the life cycle capability of the technology, and it's at a rate that is normally it's C/5, a fifth of the technology. But these are very aggressive. There's for power capability demonstrations is a 1 C rate discharge, 1 C rate charge. Again, when you start talking to a lot of application, they want there will be a good perfect charge at night, and during the day they might hit 2 C rates for a portion. The aircraft will never go down more than 30%. Will remain with 30% state of charge, just like we keep the fuel in the aircraft, as your minimum to. You land with a minimum, you're going to land with a minimum of energy capacity in your battery. 20-30% is being discussed. Those are but there's a lot of impact, as we saw on the voltage curve, for example, on your delivery of current as a result. That's a very complex issue, because when your voltage drops, your current goes up, and electronics don't like that. And if you have to have peak power and so on and so forth, so it brings complexity in your power electronic designs and so on that are tremendous. So understanding the load profile again to the industry, so what we have a very conservative way of presenting technologies, and those 1C, 1D, 100% is kind of the most aggressive. We expect better cycling ability. We've seen better cycling ability with technology by doing 94%, 95% state of charge instead of 100%, and going down to 70% depth of discharge. So keeping that 30% state of charge in there, and all of a sudden you see your cycling ability being better. So
yeah,
again, back to the point of our discussion here, and that collaboration, and thank you for reaching out. And we can help you tune that with our modeling systems, our expertise of chemistries and historical, we tune. I mean, we literally tune the percentage of these blends. Which technology that you want to maintain new car, you want to maintain power or energy, and it's all the trade-off. Like the industry has been asking us for 2000 watt per kilo, but truly it's not really that much, because there was the conditions of emergency landing, right? So if you consider the chemistry only capable to do that, a few times as an emergency landing, maybe you don't have to put this as a cycle by cycle requirements, which will improve your specific energy. So again, optimize and compromise.
Yeah. Perfect. Thank you.
Mm-hmm.
Other questions people have?
Well, I have one more
Rodolphe?
if no one else.
Yeah, go ahead, please. Yeah, please.
Volumetric expansion rates across the different chemistries is something, when you come to battery pack design and
Yep.
robustness of the cooling system within the context of keeping the welds, everything, relatively stable so you don't develop any issues with some of the interconnections, et cetera. Again, from a layperson, that's an issue with some of our design that we're working on. And so are you seeing some more stable chemistries?
Yeah,
Or
absolutely.
is it all
Absolutely.
roughly the same?
Yeah.
Okay.
Yeah, absolutely. So I was mentioning LTO gassing up, certain type of LTO, not all LTO. So LTO is an anode, okay? So the cathode, you can imagine using multiple cathode materials. You can blend these anodes, cathode, right? Based on your customizing your design. I don't know if that was clear, but that's the fact. The three chemistries that we presented, we compressed them at 2 bars. But as you mentioned, each chemistry has a swelling. So graphite tends to swell less than the silicone as you add silicone. But again, it's part of the blend, it's part of the manufacturing capability, and so on and so forth. These are what Saft brings to the table, that deep chemistry understanding that helps you integrate, your application. That's what we can discuss in more detail in terms of, when it starts swelling, why it starts swelling, and the remediation for that. Those are definitely items there. Because we do from chemistry, blending to battery system design, we have this perspective of understanding, okay, cause and effect, right? And how to remediate that. I mean, our engineering team just with the cell samples, we provide engineering integration manuals. Those characteristics are in it, the basic characteristics. We can also do digital twins. We can do modeling. We can do mechanical stress, thermal analysis, things like this to further help you out, or specific test evaluations. If you need, I said, okay, I really would like to explore this bandwidth. We published, last year, we were showing that going for 94% plus, to 100% on the NMC, contract the electrode. So if you try to further your charge state, to optimize your capacity on your battery, you're inadvertently grinding your cathode. So grinding your cathode, expose carbon, consume lithiums, damage your conductivity. It's a glued electrical system. So if you mechanically damage it, and that's what the heat does, and that's what the swelling and the cycling and all that stuff does, you damage your cycling ability. Your impedance grows, and you damage your cycling ability.
Oh, great answer. Final question, but I can relegate this to somebody else if they have a more burning question. But is lithium metal technologies? I understand right now it's the difficulty with rechargeability, and there's some things people that have briefed us where they can just replace like discs and sort of recharge via mechanical means, if that makes any sense. So maybe on the ground if you're in an airplane. But there's also rechargeability. People are looking into it, dendritic growth, and all sorts of weird non-uniform deposition of.
The dendrite formation is definitely the problem.
Yeah, exactly. So what's your take on it? Is it anywhere close? Is it a science fair project still?
No, I think there's tremendous amount of program. We have a whole group of scientists that are dedicated to that. For land vehicle, I think it becomes more of a reality. For aviation, it's with the power. If you have power requirements, the TRL is still not there.
Yep, copy that.
I mean, you're trying to immobilize something and to try to mobilize lithium across it. It's not.
I get it. Yeah, it's our assessment too. I was just curious what the leading edge was telling us these days.
Yeah, I mean, and that actually it's a very interesting question, and leading into this. The industry is leading the research. If you understand it, for these reasons of productability for scalability. It is easy to demonstrate, like to do a paper and to do, a coin sale, because that's how it's being presented at the research level. To make this into a scalable product capable to do, the whole slew of requirements that we, the few of the sticks that I showed of that is a whole different ballgame.
Concur. Yeah, thanks. Great answer.
Mm-hmm. Thank you.
Keep them coming. Anybody else got a question for Rodolphe? We talked about expansion and contraction, and that interplays with your heat output. How do we think about how that should affect the design of the aircraft to dissipate heat, especially in hot environments, or is that not much of an issue?
There is availability of criteria, airflow, altitudes that can be taken advantage of. At the end of the day, the simplicity, you're at equation of, a specific energy is difficult. Is difficult. So you can be where you can be, in the pods, in the wings, in the belly. You have to respect the center of gravities. You have to respect, your certification, certifiability of your modules. So you have also handling of quality of lithium I mean, there is a slew of criteria to be able to. It's not an easy answer. It's it's at the aircraft design. That's why all these aircraft are very, very different from one another. There is different options being taken. But again, we're working also on battery systems in EU. EU will have very strong communication in June during the Paris Air Show. We definitely look forward to be able to talk more about that and these collaboration. But yeah, I mean it's collaboration, and a lot of collaborative work can be done.
Yeah, I assume it's tricky because we have free airflow when we're in forward flight, but that's not when we're potentially dissipating the batteries and generating the most heat.
Yeah, I mean the liquid I was talking about Total Energies, specific fluids and cooling fluids. So some are using, of course, to insulate, to mitigate thermal runaway, to extract the heat. So are you doing this? You're doing this while you're charging. That's the option that Joby is doing. You have airflow, but again, you have to use look at the battery as a fuel that has a volumetric, right? It's like trying to cool the middle of your fuel tank. If you had to design something. So again, back to design. If you and that's why you see on the automotive side, those very large blade, they call it blade pouch sails, are extremely wide and thinner, so that your 3D structure kind of does not accumulate heat in the middle, right? The zone in that. So again, back to design. The swelling complexities of mechanical integrations, all this gets into. I mean, it's a complex nut to crack, and it's completely linked to how the aircraft is designed as well. So.
For sure. We have about 4 minutes left. Time for one or two more questions. Alistair, I see your hand up. Do you want to unmute and let it rip?
Yeah, thanks. From the insurance desk, we're obviously trying to model all the time the probability of thermal runaway and exothermic events for all sorts of different lithium battery architectures. A lot of it's so new that there isn't that depth of data yet. From your perspective, I wonder if you've seen a really good data source yet anywhere in the world of thermal runaway likelihood across different types of cell chemistries and architecture. I wonder what you've seen.
Well, that's the scary proposition. That's so NDA, and we can show you. We modelized all our chemistry for those very purposes. So we do chemistry model validated based on reality. we developed digital twin for these purposes. So absolutely. And it's funny because I've been presenting those capabilities, but not necessarily for the insurance purposes. And you're even though you're not a consumer of the product, you're a consumer of the predictability. And I was, yeah, I mean, let's talk, because this there will be a very good leverage for these models. I mean, we develop what we need. Those models are developed for what we produce. But definitely, I mean, thermal runaway, predictability, state of charge predictability, of course, sizing. That's a first stone on the on the requirement to size the proper battery. So we MATLAB models and so on, like that, something like this. But Total as the biggest supercomputer for the in the industry, and we take full advantage of that for I've seen some hydrogen front development, when you try to simulate an event inside a battery and design accordingly. I mean, you of course stress analysis. So we do it at the chemistry level to fine tune our blends, but to also predict thermal behavior. So I mean, let's talk some more. This is it's a very much needed tool. It's challenging to develop, but we're developing it for for what we produce, definitely. So let's keep talking on that.
Yeah, thank you. That's great. We'll connect afterwards. And I'd see a note in the chat about meeting up in Paris. We'll be in Paris. So if there is a VFS meeting at Paris Air Show, we'd love to be involved in that too.
Okay, I mean, let's connect. I mean, I'll be your point of contact, and I'm based in the US. I'm on the East Coast, but I mean, I'm talking to France. We have an R&D group in Bordeaux, France. So continuously, and either one of us, whichever is easiest for you, we can discuss. The main office, the Saft siège is at Levallois in Paris.
Excellent. That brings us to the end of our hour. And Rodolphe, I hope it's okay. I dropped your contact information to the notes. I hope
Please,
people will have a moment to grab those and get in touch with them for your one-on-one meetings.
Mhm.
And Mike Hirschberg, real quick, we had a question of whether a VFS would have a presence at Paris Air Show.
Yeah, sorry, I just answered that. So
Okay.
we don't have anything officially planned, but whenever 2 or 3 of you are gathered together, and it's a VFS meeting, right?
You're bound to break a few laws then.
No, hopefully not the laws of physics, right?
Great meeting today, Rodolphe. Thank you so much
Yeah,
for being here. Thanks
fantastic.
for your
And
continued work.
hope we get to talk again, maybe at the Electric Aircraft Symposium in July. That'd be great topic.
We had a recording from Oshkosh, and thanks to you guys and Andy to be able to present that. There was more around Saft and Total, but yeah, anytime we can produce something for you. Specific questions, will be delighted.
Outstanding.
Thank you so much.
Thanks for being here.
Great
Thanks, everyone.
session. Thank you.
Thank you.
Tom, we can finally see you now that it's over. Only now we can see you.
Yeah, finally got it working.
Good to see your smiling face.
Sounds good. Bye, guys.
Take care.